Hello! Today we are learning about Newton's first law of motion. This is going to be the first video in a set of 3 that we are learning about all of Newton's laws. Alright, here is Mr. Newton. He was the one who came up with the 3 laws of motion that we will be talking about. And these describe the motion of massive bodies and how they interact. And right now, or at this day and age, these laws, they all seem pretty obvious once we dive into the definitions of them. But at the time, more than 3 centuries ago, they were really considered revolutionary ideas.
Isaac Newton, I mean, just read his writings. The hair stands up on, I don't have hair there, but if I did, it would stand up on the back of my neck. You read his writings, the man was connected to the universe in ways that I've never seen another human being connected. It's kind of spooky, actually. He discovers the laws of optics, figures out that white light is composed of colors. That's kind of freaky right there. If you take your colors of the rainbow, put them back together, you get white light again. That freaked out the artists of the day. How does that work? Red, orange, yellow, green, blue, violet gives you white. The laws of optics, he discovers the laws of motion and the universal law of gravitation. Then a friend of his says, well, why do these orbits of the planets, why are they in the shape of an ellipse? Sort of flattened circle. Why aren't they some other shape? And he said, I don't know. I'll get back to you. So it goes home, comes back a couple months later. Here's why. They're actually conic sections of a cone that you cut. And they said, well, how did you find this out? How did you determine this? Well, I had to invent integral and differential calculus to determine this. Then he turned 26. Then he turned 26. We've got people slogging through calculus in college just to learn what it is that Isaac Newton invented on a dare, practically. So that's my man, Isaac Newton.
Yes, very impressive. So let's dive into his first law. All right, which is the law of inertia, which states an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. All right, let's dissect that piece by piece with examples. So one example that you guys have already witnessed in this class is from the PhET simulation. So an object at rest will stay at rest unless acted upon by an unbalanced force. So here we have balanced forces on either side, as you guys can see, 250 and 250. The sum of the forces, or the net force, is equal to 0. And in this example, when I hit play or go, the object did not move, or that center trolley did not move because all of the forces were balanced. Now, if you change the amount of forces, we have 350 on the left, 250 on the right, a sum or net force of 100 newtons being pushed in the being pulled in the left direction. This is an unbalanced force. Therefore, this object is not going to stay at rest because of that. It will be pulled to the left. All right, some other examples of an object staying at rest unless acted upon by an unbalanced force. You have a baseball sitting on a tee, and it will stay on that tee until an unbalanced force acts upon it, which in this case was the batter swinging. And notice that the ball went in the same direction that the force was applied. All right, now we have some student examples. This might get a little loud when I press play. So there are forces acting on the ping pong ball. There's the force being exerted by the hairdryer, and the ping pong ball would continuously go up and up and up and up and up if it wasn't for gravity holding it down. So the two forces acting upon the ping pong ball, keeping it at that same position, are the hairdryer blowing it up and gravity pushing it down. And thank you, Maggie, for the video, and James for the snapshot of you guys trying out this example. All right, now, and sorry if I keep checking the side, my iPad has been timing me out, so I want to make sure this is still recording. An object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. So we have Amy here going down the staircase.
Behold! Crushed it. Good work.
You did crush it, Amy. That was a perfect example for Newton's first law. Because Amy is going down the staircase at a certain speed and it going in a certain direction. Then she's acted upon by a wall, the wall in the middle of the staircase. That caused her to stop for a moment, therefore changing her speed. And she changed directions because the staircase took a turn. That wall was an unbalanced force. Then she came across a second unbalanced force at the bottom of the staircase, with another wall where she finally came to a halt. Thank you, Amy, for that awesome demonstration. So now there's other things that impact something's ability to stay at rest or stay in motion, and that is inertia, and exactly why Newton's law is called the law of inertia. But what is inertia? Inertia, the definition, is the resistance of any physical object to change its state of motion. We got a little snapshot of something right here about a dirt biker. He was clearly on the bike, and his motion did not really change much when his bike hit the tires. He kept going in the same direction, but the bike stopped. All right, but let's dive into more what is inertia and what things must have to have more or less inertia. All right, so the resistance of any physical object to change its state of motion. We have two examples, it's the same example, one from Liv, one from Savannah. Nice karate chop, Liv. And this was a great example of inertia. Those coins resisted the change of motion because no force was actually applied to the coins. The dollar bill was ripped out from underneath it with an awesome little karate chop, but again, no force is applied to the actual coins. So let's see if Savannah try this one out. Also a nice karate chop. Way to go, ladies. Okay, so what about something causes it to have more or less inertia? And we are going to talk about this with a home run derby question. So let's pretend we're having a class home run derby, and of course, the goal in a home run derby is to get as many home runs as possible. If you got to choose which ball you got to use in the home run derby, would you pick a wiffle ball or would you pick a baseball? I want you to pause the video and think about your answer. I hope that you chose baseball because baseballs have more mass. They also don't have little holes in the middle of them relating to their mass. But the baseball, if you were to hit the baseball and the wiffle ball at the exact same speed of like with the bat, the exact same way, the baseball is going to fly farther because it has more mass. Therefore, the property that determines the amount of inertia an object has is the object's mass. More mass means more inertia. Less mass means less inertia. All right, now let's get some practice. All right, our first example, the inertia trolley. This one, you guys are not going to have questions pop up to the side. I would just like you to read the questions and pause the video to think of an answer. Press play when you're ready for an answer. All right, for A, which trolley would be easier to push? I hope that you picked the empty trolley, because the empty trolley, there's nothing on it. It's just a trolley. It's going to be pretty easy to push because it has a lot less mass than the trolley with what looks like a bunch of really big Pepto-Bismol containers or laundry detergent. I don't know. And then which trolley has more inertia? The trolley with all of the goods on it, all of the Pepto-Bismol or laundry detergent, has more inertia because it has more mass. Example number 2. A space probe drifting to the right at a constant velocity in deep interstellar space, far from any influence due to planets and stars, with its rockets off. If 2 rocket thrusters both turn on simultaneously, exerting identical forces leftward and rightward in the direction shown below, what would happen to the motion of the rocket? So this is a pretty wordy problem, but what you guys need to learn from the first sentence is that the problem is just setting you up for a zero force situation. Because in space, there's no gravity, and then there's no influence by planets and stars, which was stated, and its rockets are turned off. So this space probe was just sitting in a forceless area. It's just really hard to picture if you don't put it in a outer space type of mindset. So we have no forces being exerted on this probe. Then at the same exact time, the rocket thrusters on the left and right side turn on with the exact same forces being exerted in those directions. So what's going to happen with the motion of the rocket? Correct answer is A. So according to Newton's first law, a non-zero net force is required to change the velocity of an object. So we had initially no forces acting upon the space probe. Then at the exact same time, we had the same exact magnitude of forces being exerted in the opposite directions. So those leftward and rightward thrusters, they are completely canceling each other out. Now, it doesn't mean that the space probe is not moving. Things can still be moving if the net force equals 0. It would just be moving at a constant velocity. All right, example 3, elevator lift. An elevator is being pulled upward at a constant velocity by a cable as seen in the diagram below. While the elevator is moving upward at constant velocity, how does the magnitude of the upward force exerted on the elevator by the cable compare to the magnitude of the downward force of gravity on the elevator? All right, so how are these forces, these 2 up and down arrows, compared? And remember that the elevator is moving at a constant velocity. The correct answer is B. If the elevator is moving with constant velocity, the net force must be 0. Okay, so again, it is moving. The elevator is moving. And if you have been on an elevator, you know that they don't normally just shoot up extremely fast and then all of a sudden go really, really slow. They normally move at a constant velocity. So they have equal forces of gravity and the cables being exerted on either side. Example 4, space probe path. A space probe is drifting to the right with constant velocity in deep interstellar space, far from any influence due to planets and stars. So again, putting that mindset in your head that there is no forces whatsoever acting upon the space probe. If a rocket thruster turns on and then off for a short burst of force in the direction that is shown, what would best represent the path traveled by the rocket after the thruster turns off? The correct answer is C, and the path is highlighted with that blue arrow. So once the net force is 0, the velocity and magnitude will now be constant again. So that's why it's not going to be the slope that is shown with B. It is also not going to be going in the same exact direction that it was going before, and it has not changed paths enough to continue going in the direction of A. So the resulting is right in between, and it is a straight linear line. All right, the car accident example. You are sitting in a car at rest when another car rear-ends your vehicle. Why do you and the passengers experience a whiplash in terms of Newton's laws of motion? I want you guys to pause the video and think about your answer. Press play when you are ready. So now that you have thought of your answer, I want you guys to choose A, B, C, or D from this list. So the correct answer is D. An object at rest tends to stay at rest. Right? So you didn't want to move. You were happy, you were content, your body, your neck, all wanted to stay exactly where it was. But because that car hit you from behind, there was a force, an unbalanced force acting upon you, causing your body and neck to kind of whip, resulting in whiplash. All right, 2 more. Example 6, inertia comparison. Which object, pictured to the right, has more inertia? So a bowling ball or a tennis ball? A bowling ball has more inertia. A bowling ball has more mass, therefore it has more inertia than a tennis ball. Last one, another inertia comparison. Which object pictured to the right has less inertia? The feather has less mass than a hammer, therefore it has less inertia than a hammer. All right, thank you for watching, and this is Mrs. Hilt signing off.